Good morning, Britain. Today's top story: a group of young aeronautical engineers from London's Imperial College have made a revolutionary step forwards in renewable energy generation. To tell us more about it, let's hand over to Vincenzo.
Thank you, Williams, for the introduction. Now, on to the objectives of the project. So, they were the designing, making, and testing of the most efficient wind turbine that we could, given the determined constraints, which follow. So the first one was, it was a horizontal axis design with a clockwise rotation with respect to the wind direction. Second one was a maximum angular velocity of 3000 RPM with maximum power coefficient obtained at a TSR between 3 and 8. Now, there were 4 tests predicted at 6, 8, 10, and 12 meters per second, which unfortunately couldn't happen due to coronavirus. And the maximum diameter of the turbine was meant to be 450 millimeters with no restriction on mass. However, the biggest constraint was given by the 3D printing area, which is 400 by 150 by 100 millimeters. Now, this caused the biggest design challenge because we had to maximize the size of the turbine without exceeding the limitations given by the printing area.
Thank you for that, Vincenzo. Now that we know what this project is all about, let's speak to the group's aerodynamic design specialist, Shaun. Shaun, why don't you tell us a little bit about the aerodynamic design considerations?
We selected the most suitable airfoil by comparing a range of designs based on their maximum CL/CD value, its corresponding optimal angle of attack, and overall stall characteristics. The airfoil had to exhibit a relatively gentle stall and have sufficient buffer between the optimal and stall angle of attack. Given these constraints and objectives, we decided to go with the SG6043 airfoil. The same airfoil section was used throughout the blade to avoid geometric discontinuity, which may have hastened the onset of boundary layer separation. Calculations using wind tunnel testing conditions yielded an approximate Reynolds and Mach number of 50,000 and 0.03 respectively. Inputting these parameters into QBlade generated plots which showed the expected performance of the SG6043 airfoil at various angles of attack. Notably, SG6043 had a peak CL/CD value of 39.8 at an angle of attack of 8.5 degrees. Further visual analysis confirmed that at an angle of attack of 8.5, the boundary layer was kept thin along the chord and only began to separate very near the trailing edge, leaving behind a small wake.
Thank you for that, Shaun. Now that an airfoil section has been selected, let's hear from another of the group's aerodynamic specialists, Wei. Wei, why don't you tell us a little bit about blade optimization?
With our selected airfoil, we had to calculate our target TSR, chord distribution, and blade twist angle. We start with actuator disk theory, which tells us that the power coefficient achievable by a wind turbine is 0.5926, also known as the Betz limit. Furthermore, it tells us that there is an optimum ratio of wind speed through the rotor plane to U infinity, given by A equals to 1/3. To optimize our wind turbine for this TSR, we had to calculate the optimum blade twist as well as the optimum chord length at each section. The optimal chord length could be found either using the Betz model or Schmidt's model. The Schmidt's model was chosen as it accounts for the rotation of the wind via the tangential interference factor A', giving a more accurate representation of flow past the turbine. This thus produces the chord distribution as shown. Blade twist must be applied to optimize the effective angle of attack at each section of the blade, due to the different tangential velocities at varying distances from the center of the turbine. While velocity normal to the blade, U infinity, remains relatively constant along the blade, tangential velocity decreases as we approach the root, resulting in different effective angles of attack. Blade twist was calculated iteratively via blade element momentum theory using MATLAB. A tip loss correction factor was added to account for the finite number of blades and effects of the wake. We decided not to incorporate design elements like vortex generators and dimples because these were too small to have a significant impact at the scale we were printing at.
Now that the blades are aerodynamically efficient, they must also be able to withstand the loads during operation. Let's hear from one of the group's structural engineers, Wing. Wing, why don't you tell us a bit about the structural design considerations?
Thank you, William. First, we consider the main forces acting on the blade, which are the lift, drag, and centrifugal forces. The bending moments can be calculated by multiplying the force and the moment arm associated with it. In our analysis, we have neglected a few terms. Bending loads from Wei, stagnation pressure, inertial forces, and torque are all very small at the operating conditions. The ABS plastic is stiff, and so resonance is unlikely. For aeroelasticity, I do not know how to calculate it, so let's also ignore it. Because the blade has a non-uniform shape, we discretize it into sections using BEM theory and calculate the forces acting on each. We already have the lift and drag data from our colleagues over in Singapore, and so the centrifugal force of a non-uniform blade can be calculated by the following equation. The stresses can be found simply by dividing the forces with the areas. In the graph shown, the blade is very safe within the material limits. Next up, we have to make sure the blade is securely attached to the nose cone. Using the following equations, the stresses at the roots are found to be within acceptable limits. The 6043 airfoil section that we are using is rather thin, so we have decided to wrap the airfoil around the nose cone to maximize the interfacial area, minimizing the chances of it breaking off. Finally, we use the virtual work method at each section to check that the blade does not deform significantly, and the results are surprisingly small. The maximum deflection occurs at the wingtip, which is 0.1 millimeters. Now we know that the blade will not break. The design is now ready for manufacturing.
Given a solid aerodynamic and structural design, it must be possible for the turbine to actually be produced. In charge of 3D printing, let's hear from Vincenzo.
So using a dual ball and socket hinge, which was commonly nicknamed as dog bone. Now the dog bone allowed for the nose cone to be printed open, only to be then sanded and epoxied after in the workshop. This is the exploded view of the nose cone. Whereas this is the exploded view of the nose cone with the back view of the closed nose cone after being epoxied, looking at the dog bone, the inside where the hub stood, and this is how it was printed. Now, it was printed open, and the dog bone was free to move, so it could be closed, it could be epoxied properly, and it could be closed as shown. Now, to construct the blades then that was attached, the airfoil file with the twist angle and chord length was imported to create the wing that was then designed and explained by my fellow colleagues.
Thank you very much, Vincenzo. That's very interesting. So, let's talk about the manufacturing of the wind turbine. Now, as we understand it, the hinge mechanism allowed it to be assembled very easily, glued together to create the wind turbine shape. However, there were blemishes due to the 3D printing, and these had to be sanded down. Now, let's listen to Shaun, who's going to talk to us about the simulation of the wind turbine.
With our blade fully defined with chord lengths and twist angles, the Q-blade simulator indicated that we were theoretically supposed to achieve a peak pressure coefficient of 0.401 at a tip speed ratio of 5.9, which is about 2/3 of the BET's limit. Our original TSR was calculated to be 2 pi, as that was deemed to be the ideal ratio for a two-bladed wind turbine. However, we eventually decided on 5.9 based on the simulation. Furthermore, there is a modest plateau for the CP values across a range of TSR 5.3 to 6.3. Thus, 5.9 is an acceptable middle value. Unfortunately, we do not have wind tunnel testing data because of the current circumstances. So this and the other aerodynamic data mentioned earlier were the only available estimates on the performance of the turbine.
Thank you, Shaun. I for one are very proud of these students for getting involved in such an interesting, challenging project. And although they didn't get to test it, I'm sure they would have done very well. Have a good day.